So let's get started, please. So we're talking about the singular value decomposition, right? Very useful applied technique. So remember what the thing is that you have singular value decomposition. You have a rectangular matrix with m bigger than n, bigger than or equal to n, and you have an orthogonal n by n matrix. You have an orthogonal n by n matrix, and you have this basically something like a diagonal matrix. Okay, it's not diagonal, but it's rectangular, and in the upper part, in this upper square up here, it's diagonal. So it's 0 down here, and then it's diagonal up here. Okay, so it's basically like something like a diagonal matrix. Okay, and right, sigma 1, sigma 2. We denote these guys by sigmas. And singular value decomposition. So here's how to say it. If there exists, so you start off with some matrix. If there exist these matrices, these orthogonal guys and this diagonal rectangular guy, such that A equals U sigma V transpose, then we call this thing a singular value decomposition of A. Okay. Remember what orthogonal means, right? Orthogonal means that U transpose times U is the identity. That's to say that U transpose is the inverse, right? U transpose is the inverse. V transpose is the inverse of inverse matrix. And so one way you could think of this is maybe as some sort of generalization of the spectral theorems, right? Because for our spectral theorems, right, if A is square and symmetric, then we know that there exists an orthogonal matrix such that U, T, and U is actually diagonal. Right? We didn't prove this, but we mentioned that it was true. The one we did prove was the complex for Hermitian matrices, right? We showed that for Hermitian matrices you have something like this. It's also true for symmetric real matrices, that they are orthogonally diagonalizing. Okay, so you see what it is, right? You've right. A then is this U D U transpose, right? And so you have this decomposition, right, where you've realized A as a diagonal matrix, and you've got these orthogonal guys on the left and right. Okay. And so this is some sort of generalization of that for rectangular matrices. Okay. But it's true for not just for symmetric guys, but for all matrices. So, so the theorem is that everybody, right, any A R M plus M has a singular value decomposition. Okay, so the the proof of this is a bit laborious. So get ready and put your hands on your. You can put your hands on your head on your hands right now, just to support yourself. Okay, but in any case, here we go. It's going to be a little bit laborious, but try and bear through it. And then afterwards, I'll try and say something that will make it a little bit clearer. Okay, but here's so here we go. Part one, we're going to construct. Part one, let's construct V. Right. We want some sort of decomposition. Some way of factoring your matrix into something like this. We're gonna build it. Okay? We're gonna build it ourselves. Okay. So part one. So first observe that ATA is symmetric, and so all the eigenvalues are real. And then notice that the eigenvalues of ATA, in fact, are all non-negative. Maybe I'll let you try and work out this thing here. Take 2 minutes and see if you can figure out why all the eigenvalues have to be non-negative.
I was trying, yes. I think symmetric means you equal the transpose, right?
Is equal to A.
A equals AT.
ATA equals AAT.
Yeah. So then you get the T.
A equals AT.
So then you do, yeah. Or would it, yeah. No, but when you do the transpose, don't you do the... Wouldn't you start with this one?
No, that's Hermitian.
But that's Hermitian?
Are you doing conjugate transpose?
It's like
yeah.
AB.
We're working with
T
real
equals
numbers.
B.
Is that how you break it down? That's how, I mean, that's how you take the transpose of a product of matrices. Yeah. But
This is a
product.
Wait.
ATA is a product of matrices.
Which is like, it's just like saying...
Right. So the transpose of ATA is ATA.
Yeah, that's what I was going to say.
Yeah.
Okay. Which somehow... Does that mean this?
This is a little bit. I don't know if this maybe involves sort of a trick. So I don't know if anyone will have an idea of how to see this. Does anyone have an idea of how to see this? Here's one way of seeing it. Let V be in the eigenspace corresponding to some eigenvalue. So lambda is some eigenvalue. Okay, and then let's look at the inner product of ATAV against V. Okay. does everybody see that this is the same thing as this, right? Because remember, what do you do when you take W transpose against V? Right. So this is going to be V transpose against AV. Right. But V transpose against AV is the same thing as AV transpose AV. Right. Which is this thing on the right. If you have right, so when you can pass this matrix over to the other side as long as you take the transpose of it. So this AT turns into A transpose transpose on the other side, and so we get AV. Okay. So let's look at that. But this is the same thing as lambda v, right? Because v is in the E sub lambda eigenspace. And I'm going to pull the lambda out. So I pull the lambda out, and I see that I can realize that lambda is going to be AV over VV. Right, and these things are both positive, right? V is not a zero vector, so we can divide, and this is going to be non-negative. Okay, so the eigenvalues are, we have non-negative we've got all non-negative eigenvalues, and let's order them. Order the eigenvalues so that they are decreasing. Lambda 1 is bigger than or equal to lambda 2, is bigger than lambda n, which is bigger than or equal to 0. Some of them might be 0, but who knows? They're all bigger than or equal to 0. Okay, everyone with me so far? Okay. Nothing amazing has happened. Okay, so now ATA being symmetric is orthogonally diagonalizable. Okay. So that is, there exists a V, an orthogonal matrix V, such that V transpose ATA V is diagonal, and we can assume, without loss of generality, assume V is these columns are well, let's say it like this. these columns are in such an order as to make D like this. Okay, so we're gonna. It may be, you know, however you order the columns, you're going to get the corresponding eigenvalues, right? If V's first column corresponds to lambda 2, then when you conjugate, then when you do this diagonalization, you get the lambda 2 up here. But let's just reorder the columns so that they correspond to the eigenvalues in decreasing order. Okay, so reorder the columns so that they correspond to the eigenvalues, right? So let's reorder columns so that they correspond to the eigenvalues in decreasing order. Okay. Okay. So that V is actually going to be the V that we want for our singular value decomposition, right? That V is going to be this V. Okay. So at this point, let's just hold on to that V. Okay. And now we're going to construct sigma. So since 98 is symmetric, we know its rank equals the number of non-zero eigenvalues. Its rank equals its number of non-zero eigenvalues. Let's say that there are thus we're going to have R non-zero eigenvalues, and then you're going to have a bunch of zero eigenvalues. So basically, all we're saying is that let's let R denote the number of non-zero eigenvalues. Okay, and then so you're going to have this many non-zero eigenvalues, and then you're going to have a bunch of zero eigenvalues. Then take sigma I to be the square root of lambda I, and let sigma 1 be the R by R matrix that has sigma 1 through. It will be an R by R diagonal matrix that has sigma 1 through sigma R down the diagonal. And let sigma be sigma 1, 0, 0, be the m by n matrix that has sigma 1 in the upper corner. So you know, this should be sort of mysterious at this point. Like what you know, why is this what we want? It'll become clear in a second. You know, we're doing this construction. You know, at this point, you know, maybe it's not really clear why we chose why we're choosing these things, but I'm hoping in a second you'll see how it all fits together. Okay. So, any questions? Yeah, Mia.
For sigma, is it like m zeros by n zeros, not just a 2 by 2?
Oh yeah.
Oh.
Yeah. So this is
I think there should just be
these guys
little
are
dots.
zero. These guys are zero matrices. So this is an r by r here, right? This is m by n.
Okay.
Okay. So this here you've got a diagonal matrix here, and then here you've got a m minus r by n minus r zero matrix. Here you have an m minus r by r zero matrix, and here you have a, you know. Sorry, I messed up the first one. So this is
Yeah,
anyway. Yeah. Yeah. Okay, you see what I mean. Yeah, it's an m by n matrix. There's an r by r diagonal matrix, and then zeros everywhere else. Okay. Okay. Give me 1 second to see if I can think of a better way to so I could possibly go a completely different way that might make more sense to you guys. Okay, so you guys are looking kind of dulled by all this notation. So hold this for a second. Okay, stop right here, and I'm gonna try and explain what's really going on. Okay, I'll try and explain what's really going on, and then we'll come back to it. Okay.
Can we write it down?
Yeah. You can write down what I'm gonna write here. So let me see if I can make this give some sort of strategy to what we're doing. Okay. So what's really going on? What's really going on here? Okay. So here's the idea. One, we know ATA is symmetric. Right. So there exists an orthogonal V such that B transpose A transpose AV is diagonal, right? This thing is diagonal. It's diagonal. It's going to look like this. 0 is here. We know there's an orthogonal V such that this happens. That's basically what we're saying here. Okay. Where R is the rank of ATA, which we showed last time is the same thing as the rank of A. Just recall that. And the eigenvalues are all non-negative, and we assume they're decreasing. Right? Without loss of generality, we can assume that they're in decreasing order. Okay. Let V1 be the first R columns of V. So let V1 be the first. Let V1 consist of the first R columns of V. Okay, so you make this matrix. Right? You have this orthogonal matrix, and you have this orthogonal matrix V, and you take the first R columns of it, and you call that V1. Okay, so V is like this. The first R columns are going to be V, and then the last n minus R columns we're going to call V2. Okay. So what we're saying is that what we have is that if we take ATA and multiply on the right by V1, V2, and multiply on the left by V1 transpose, V2 transpose, then we get this this diagonal matrix, right? We get this diagonal matrix and then the zeros. Okay, so right. Okay. At this point, you make some observations. You observe what happens if you take V1 transpose V1. Right? So remember, V1 is an n by R matrix, right? So you take this R by n times an n by R. And what happens if you do that? Yeah, you do, certainly. But something better, right? This is V. Remember, V is orthogonal, right? So what are you going to get? You're going to end up with the identity matrix. Yeah, you're going to end up with the R by R identity matrix. Right? Are you okay? Okay. Okay. What happens if we take V2 transpose V2? Again, this is going to be V2 is n by n minus R, right? Remember those columns? N minus R times n, right? Again, of course, you're going to end up with an n minus R by n minus R matrix. Right? And what will it be? It'll be also the identity, right? Also the identity. So, and then the last observation we make is this. If you take V1 transpose and add on to it V2 transpose. Okay, so this is now n by R by n. This is n by n minus R, and minus R by n.
Would you just get 2i?
No. think like this. So if I take here's V, V1, V2, V1, V2, and I take V1 transpose, V2 transpose. Okay, right. That's to say I take V times V transpose. I know that that's going to be I. Right? I know that that's going to be I, right? Because V is orthogonal. Right? Okay. But what is this? What do I get? Actually, this is the same thing as V1 transpose plus V2 transpose. Right? If you work it out, right, you're going to be going, right, just by the laws of matrix multiplication. If you have like this matrix and this matrix and this matrix and this matrix, then you're going to end up with AB plus C, AC plus BD, right? Just by matrix multiplication. Okay. So you don't end up with 2I, but actually just 1I. It seems a little peculiar, but this is also I. Okay, everyone still alive? Everyone okay? Any questions so far? Yeah, and Andrew.
What is like the actual V matrix?
The actual V matrix is it's this orthogonal guy that you get from the spectral theorem.
Okay.
Right? It consists of, if you may recall, it consists of the eigenvalues that correspond to the it's the eigenvectors that correspond to the eigenvalues of ATA. Okay. Yeah, Mia.
And it has some eigenvectors that correspond to 0 eigenvalues.
Right. So
that's where the V2 is. That's what the V2 is.
Yes, that's right.
Okay.
That's right. Yeah. So the V2s are the eigen. Exactly. The V2 consists of eigenvectors corresponding to eigenvalue 0. These guys correspond to the non-zero eigenvalues. These guys correspond to the 0 eigenvalue. Great. Okay. Everyone's still on board. Okay. So you make these observations, and you say, okay. So this will give you a sense of sort of how the SVD sort of works. Okay, so you take the orthogonal matrix that diagonalizes the symmetric ATA. Okay, and you make these observations, and you say, well, okay, now let U sub 1 be A B1 be the negative half. And this is going to be in R n cross R, right? Because A is in m by n, V1 is n cross R, and D was a diagonal guy. And what I mean by taking the negative square root, all I mean is that you take the square root of each of the elements down the diagonal. Right? It's a diagonal matrix. Just take the negative square root of the diagonal elements. Okay. For diagonal matrices, it's easy to define like the square root of a matrix, right? If you have a matrix with diagonal elements, then if you just take the square root of the diagonal, you multiply these guys together, right? If I call this d to the 1/2, it makes sense because d to the 1/2 times d to the 1/2 is going to give me d, right? So that's what I mean by the square root. And here's the negative square root. So you just take the negative square roots down the diagonal. Okay. So okay. So let U1 be this guy. Then U1. So we're gonna make sort of a lame version of the SVD first. Okay. So this is sort of like a fake SVD. U1 d to the 1/2 V1t. Here it is. U1 d to the 1/2 V1t. What does that give us? That would be, well, U1 was a V1 d to the negative 1/2. And then we have this d to the 1/2 V1t. Right? D to the negative 1/2 times d to the 1/2 is going to be 1, right? The identity matrix. So you get a V1 V1t. Okay. But I can rewrite this as a V1 V1t, a V1 V1t plus V2 V2t. Why is that okay?
Because we just the identity matrix.
It will be the identity matrix, but why can I just
By matrix
lightheartedly?
multiplication.
What happens when I take a times this guy here, a v2? Mia, you can probably get this one. I'm sure you know the answer to this. What happens to a times v2? What did you notice about v2?
It's the, is it 0?
It's 0,
Okay.
right? Because v2 consists of the eigenvectors corresponding to eigenvalue 0, right? So when I hit this thing with a, I don't even get over to here. By the av2 itself is 0, let alone av2 v2t. Okay, so throwing this in doesn't change anything. I've just thrown in a 0. Okay, but you see why that's good, right? Because this thing we just saw is the identity matrix, right? So you get a. Okay. Right? In other words, we get that A can be decomposed into this this U1 d to the 1/2 V1t. Okay, which is something sort of like what we want, right? It's not exactly what we want. We really want this thing to be orthogonal. We like this thing to be an orthogonal matrix. It's not an orthogonal matrix because it's not square, right? This is not square, and this is not square, right? This is m by r, right? And this is r by n, right? But this is something like the SVD, and all we need to do to make the full-blown SVD is to basically fill these guys up, fill up U1 and fill up V1 to get orthogonal guys. Yeah, Mina?
Is that why V equals that? So you can fill it up with zeros?
Yeah. So we'll basically fill up the V1 by adding on V2 to it, and we'll fill up the U1 in some way that we'll show next time, I guess. Okay. And when you do, what you get is that A is expressible as an orthonormal guy times this diagonal guy times this orthogonal guy times the diagonal guy times the orthogonal guy, and that's the singular value decomposition. And notice what this D is, right? It's D to the 1/2, right? It's this D with everything to the 1/2, right? So it's right? It's this thing, which we were calling which we were calling sigma 1 before, right? This is the sigma 1 that we mentioned before. Okay, so this is the idea, right? That that ATA being symmetric gives us this matrix which diagonalizes it, and then if we choose cleverly, we can break A we can break A itself into this form. Okay. This thing here is called the compact SVD. Okay, so it's like a baby version of the SVD. It actually has all the information that you want.